In today's video, we're going to look at the mean. So we're going to look at both sample means and population means, and just some notational things that go along with that, as well as expected values when we are looking at probabilities. So first of all, I want to look at sample means. So a sample mean is where you take a sample of particular things. In this particular example I'm going to look at, we are looking at cars and weekly sales of cars. We've looked at this problem before. And then I am going to look at what is the mean of that sample. So in this case, what is the mean amount of weekly sales for cars for this particular dealership? Okay. So for a sample mean, whenever you try to denote that, you always use this term X bar. X bar is what is used to denote the sample mean. And in order to figure that out, you just add together all of your data points from your sample and then divide it by the number of things that are in your sample. Okay. Let's do that for this particular problem. So I'm looking for what is the mean amount of weekly sales for this car dealership. Now, we've got this in a frequency table, which I'll talk a bit more about in a second. But when you figure out the sample mean for this problem, you're going to add together all of the weekly sales and then divide it by the number of weeks that there are. So I know that I've got 2 lots of 5 sales a week. I've got 2 lots of 6 sales a week. Then I've got 13 weeks where I had 7 sales. So I'm going to have to add together 7 13 times. And I'm going to keep going with this. Then I've got to add 8 20 times, and you're going to keep going with this. Okay. And then you divide that. We're looking at weekly sales for the year, so there's 52 weeks in the year. When you do that, the value that you come out with is 7.96 if you round it. So we know that the average number, the mean number of weekly sales for this particular car dealership is 7.96 sales a week. Okay, that's the average number of car sales in a week for this dealership. So whatever problem that you get, whenever you have a sample, this particular problem is a sample because we are only looking at a year's worth of data. So we only have 52 data points out of a whole bunch of data points for the entire time that this car dealership has been open. Okay, so we have just looked at the weekly sales for that year. So we've taken a sample of data, just 1 year's worth of data from this dealership. We've added together all the weekly sales for the entire year and divided it by the number of weeks in the year. And that has given us the average number of sales in a week for this car dealership. Okay. Like I said, this is a sample mean because we have just taken a year's worth of data. We've just taken 52 data points out of however many weeks this car dealership has been opened. Okay. There is also a population mean. The population mean would have been if we had every single weekly sale for this car dealership for the entire time that it had been open. That would have been the data as a population, not just a sample of 1 year's worth of data points. Population mean is calculated in very much the same way, except this time it's denoted by mu. Mu is a Greek letter. Okay. And mu is just, again, it's going to be all of the data points from the population this time added together, divided by the number of things in the population. We tend to denote the number of things in the sample by a small n, a lowercase n, and we tend to denote the amount of things in a population by an uppercase n. So they're still calculated in exactly the same way. It's just a notational thing that you have to be aware of. Whenever we deal with anything to do with samples, so we call them numerical descriptive measurements, But whenever we figure out any kind of numerical value that deals with a sample, it is called a statistic. Okay, so the sample mean is a statistic because it is a numerical value that represents something to do with a sample. It's called a statistic. Anything that is a numerical value that is used to describe something for a population is called a parameter. This will also come up again when we look at variance and standard deviation in our next section. But anything that is a numerical value used to describe a sample is a statistic. Okay, that's actually what we use the word statistic for. Okay, and then anything that's used to describe a whole population is called a parameter. So the population means a parameter and the sample mean is a statistic. I now want to go back and look at this frequency table. Okay. This is just a frequency distribution for this car dealership. And we looked at this before, and then we figured out a relative frequency distribution for the same dealership where we took each of the number of occurrences and divided it by 52. So that was its occurrences relative to the whole sample, the whole 52 weeks of the year. So we would have had the relative frequency of 5 weekly sales would be 2 out of 52, 1 over 26. Okay, so you can also do this as a relative frequency distribution, but let's look at this as a frequency distribution right now. Another way that you can calculate the sample mean, which you can see from here, is going to make sense because it's exactly the same as what we actually did. But whenever you've got a frequency distribution table, you're going to take each one of your data points, so each one of your weekly sales, 5, 6, 7, 8, 9, 10, and 11, you're going to multiply it by its frequency and divide it by the number of things that you have in your sample. Okay, so we're going to do this the whole way along. Why does this work? Well, it's exactly the same calculation that we did before. Let's look at the calculation we did above. We took 5 multiplied by 2 divided by 52. That's the same as doing 5 plus 5 divided by 52. Then we would take 6 multiplied by its frequency of 2 divided by the total number of things that there are in my sample, which is 52, which is the same thing as 6 plus 6 divided by that 52. And then the next one would be 7 multiplied by its frequency of 13 divided by 52. Well, that's the same as adding 7 to itself 13 times and then dividing it by 52. So whenever you get a frequency distribution, rather than sitting there and adding together every value, just take each of the values, multiply it by its frequency, divide it by the total number of things that are in your sample. So it would be x1 multiplied by its frequency f1 divided by the total number of things in the sample. If you have a relative frequency distribution where you would have taken each of these frequencies and divided it by the total number of things in your sample, so for each particular weekly sale we have its relative frequency, so its frequency compared to the whole thing, you would have just multiplied each of those data values, so x1, x2, x3, etc. Just multiply that by its relative frequency. It's the same calculation. Okay, so if you have a frequency distribution table, take each of your data points, each of your x values, multiply it by its frequency, divide it by the total number of things in the sample. If you have a relative frequency distribution, take each of your x values, just multiply it by the relative frequency. They've already done that division of dividing it by the whole thing anyway. Okay, so if you've got a relative frequency distribution, just multiply straight across and add together. Okay, so I would have done 5 multiplied by 2 over 52, plus 6 multiplied by 2 over 52, plus 7 multiplied by 13 over 52, and keep going. Okay, so frequency distribution, each of your x values, multiply it by its frequency, divide by the total number of things in the sample. Relative frequency distribution, each of your x values, just multiply it by the relative frequency and add them all together. Okay. The same thing would work for the population mean. So if you are trying to figure out the population mean, so not just for this sample, let's say we had a whole population's worth of data, then you would do the exact same thing. You take each of your data values, multiply it by its frequency, divide it by the total number of things in the population. And you just add all of those together, and that again will give you the population mean. So I'll quickly write that down. You would take, if you had a frequency distribution, you'll take each of your x values, multiply it by its frequency, divide it by the total number of things in the population. And you do that for each one of your data values. Like I said, this is more of a notational thing, but the actual mean is calculated in the same way. Next, I want to look at something called expected value. And this time we are looking at probabilities. Okay. Let's say, we've again looked at this example before. Let's say that you are given the problem that you are going to toss a coin 5 times. And you're going to see what the probability is of a certain number of heads out of the 5 tosses of a coin. So again, like I said, we've looked at this before. So when you toss a coin 5 times, you could end up with 0, 1, 2, 3, 4, or 5 heads, depending on what happens. And we need to look at the probability of each one of those outcomes. So again, we've already done this. We looked at the probability of no heads out of the 5 tosses of the coin, 1 head out of 5 tosses of the coin, etc. So that's what this column looks at. It's the probability of each number of heads, where k is the number of heads. What I want to look at is what is the expected number of heads out of 5 tosses of a coin. To show that this works, I'm going to first think about this logically, because this is a very good example to see logically why this works, and then you can just do the actual mathematics for any example that you get where they ask for the expected value. Normally we look at expected values of a game, which is where game theory comes in, and I will do a video or two about that at the end of this course. Like I said, it won't be tested on, but it is kind of a good application of this stuff. But in game theory, a lot of the time they will ask you, what is the expected value of a game? In other words, a lot of the time it's how much would you expect to win or lose when you play a particular game, given the probabilities of the game. So for this particular, we can call it a game, tossing a coin 5 times, we're looking at what's the expected number of heads. Well, if you toss a coin 5 times, you've only got heads or tails. And if it's a fair coin, you would assume that 50% of the time you would get heads and 50% of the time you would get tails. So out of 5 tosses of the coin, and again, I know that this is not possible, but in terms of mathematically, you would assume that half the time you get heads, half the time you get tails. So out of 5 tosses of the coin, you would assume that 2.5 times you would get heads and 2.5 times you would get tails. So mathematically, that's what we're looking at. So I would expect my answer to be 2.5 here. Okay, that is indeed the answer. But how do we get that? In very much the same way as when we were just dealing with means, this is why we talk about this here, because it is basically looking at what's the average of the game, what's the mean of the game, okay? The expected value is just where I take each of my outcomes and multiply it by its probability. And then I add them all together. So I take each one of my outcomes, multiply it by its probability. And this is what this column is here. So I've taken 0 times 1 over 32 is 0. 1 times 5 over 32 is 5 over 32. 2 times 10 over 32 is 20 over 32, etc. So whenever they ask you for the expected value of a game, the first thing I want you to do is to take each of the outcomes, multiply it by its probability in this probability distribution. Okay. Then, once you've got each of the outcomes multiplied by its probability, I just want you to add all of these values together. Okay. And when you do that, that will give you the expected value of the game. Okay. So the expected value, we tend to call it E of X, okay? It's the expected value of the random variable X. Remember I told you that random variables would come up again in notation, and this is one of those times. Expected value of your random variable X. What is the expected value that we expect that random variable to take on out of our outcomes, okay? So all you do is you take each one of your outcomes and multiply it by its probability. And you do that, I'm actually going to do that as an uppercase N. You do that for all of your outcomes. Now, we tend to denote this as an uppercase N for the number of outcomes just because we are looking at all possible outcomes for this particular game, okay? So if we are looking at all possible outcomes, therefore it's a population because we're not just taking a sample of outcomes, we're looking at all possible outcomes. So because of that, they treat it more like a population, and therefore we use an uppercase N in order to denote the number of things that are outcomes, okay? So then you just add together all of those outcomes multiplied by their probabilities, and that gives you the expected value. We normally use E of X as the expected value to notate that, but you will occasionally see it as mu because, again, you are pretty much looking at a population mean here. Okay, you've got all possible outcomes, which means that we're looking at a population because I'm not looking at just a sample of outcomes here. So I've got all possible outcomes, and I'm basically figuring out what the mean of the outcomes is. So they sometimes use mu to denote it, but most of the time it will be E of X. If you are ever given a histogram of this data, again, if we think about this logically, it should pretty much be where the midpoint of your data is, okay? Your data should be balanced either side of your mean. Now, it may not be the absolute central data point like a median is, but it will be the center of your data. So wherever most of your data is kind of accumulated, it should be around there. You should have a balance on either side of your mean, where you have some of the smaller values below, some of the bigger values above, and it should be somewhere central to your data. So we kind of tend to think of it as a balance point more than just like the center of the data. So just kind of be aware of that. If they ever give you a histogram and say, roughly where is the mean, think of it as a balance point.